Okay, we're down to our last convergent boundary type, and that is continental to continental. Okay, so we're going to use green this time. I'm going to use two different types of green to show two different continental plates colliding. This is going to be a little bit more complicated than our other convergent boundaries we've drawn so far. So I'm going to start with just a bottom line for this continental crust, and we're going to make it really thick. We're going to make it a really thick continental crust. It kind of trails back off there at the edge. Okay, and it's going to come up to a peak because convergent continental to continental make the tallest mountains in the world, like the Himalayas. The Himalayan mountains are some of the tallest in the world. They're also some of the youngest mountains in the world. Okay, so we've got this green coming up to the peak of the mountaintop, all the way up here. Let's kind of color in a little bit of that on this side. Leave this part still blank. We're going to come back and add some details on that here in a moment. Okay, so we got. So this side would kind of be like the Tibetan plateau of the Eurasian plate, where the Himalayas are forming when the Indian plate is colliding into the Eurasian plate. It's got a high plateau on the back side, on the north side of the Himalayan mountains. We'll get to why that occurs here in a second. Okay, so we can have some little hills and stuff mixed in here. Because the continents aren't nice and flat. There's topography to it. Alright, so that finishes out that side. Now, I'm going to use a lighter color green for the other continental plate. And it's going to come down a little bit like this. And it's going to come back up and trail off to the other side. We're not going to make it quite as thick. It's going to be a little bit thinner continental plate, but it's going to come up and it's going to join at the top here, just like the other side. So we've got two different continental plates colliding together, and a mountain right where they're slamming together. There's a giant, very tall mountain. Some of the tallest mountains in the world form this way. So what's interesting, if you want to climb the tallest mountain, or rather the highest elevation mountain, I should say, because it does matter how you measure the mountain. The tallest mountain in the Himalayas is not always going to be at the same elevation it is. It's actually still building because the Indian plate is still sliding into and colliding with the Eurasian plate. It's going to keep growing. I think it grows at about an inch a year. So if you want to climb the tallest mountain and be the person who's climbed the highest elevation mountain, you've got to keep going back because it's continuing to grow. All right, now we're going to kind of mix this light green here over into the other green as well. And then I'm going to come back and I'm going to blend these two together because that's exactly what happens in the real world. When two continental plates collide, the rocks that make them up get mixed up. The tectonic forces of this collision not only force the rocks upward, but they force them into each other. And that process makes amazing folds and twists and turns in the sedimentary rock. It metamorphoses the rock that's inside them. And sometimes there's even leftover pieces of ocean plate that comes up into the other. So now we're going to have a nice kind of sloppy center here in between these two continental plates because they're getting all mixed up. They're getting all mixed up when they form this giant tall mountain. Let's make it a little bit taller. And young mountains, they're always very steep-sided because erosion has not whittled them away. We've got the Smoky Mountains here in Kentucky, in eastern Kentucky. They're really old mountains. When you compare them to these, they just look like hills. They're not very tall. All right, so there's our two continental plates colliding. We're going to add a few more things in here as we continue. So let's add a few more things to our continental to continental. We cannot forget the very bottom of the lithosphere, which is the uppermost part of the mantle, remember? But also, there used to be a little piece of ocean stuck to the bottom of this plate. So let's add a little ocean crust that's subducting down underneath. Okay, now when two continents collide, neither of them want to subduct because they're similar in density. And that's why instead of going down, all the rocks are forced up and form those mountains. Okay, but there used to be ocean between those two continents when they collided, so we're going to add a little old ocean crust there. Okay, and right under that is the bottommost layer of the lithosphere, and that is the uppermost layer of the mantle. We're going to add it back in red, like we have been. Okay. And it's going to follow along with this old ocean crust going down below. And some of that old ocean crust is still melting and bubbling back up. So we do get a little bit of upward travel and sometimes some igneous intrusions into these mountain ranges. So mixed in here, sometimes we'll have a little granite along with the folded limestone and sedimentary layers. A little bit of mixed in igneous intrusive to that mountain range. But they're so thick, that continental plate is so thick, it doesn't actually burst the surface here. It doesn't make a volcano like our others. It just makes a layer, intrusive igneous rock, rather. Not a layer. Sedimentary rocks make layers. Alright, but these sedimentary rocks that were on this continent, okay, have been metamorphosed, twisted and turned, and they're folded and stratified weird ways, making this really tall, really, really strong mountain range. Okay, but we do have some upward movement of lava, magma rather, coming back up. Sometimes. Alright, so we have old ocean plate coming down, subducting underneath this collision. And of course our arrows showing the convection in the asthenosphere. Okay, and it's diving down here. That's that mantle convection once more, causing this slab being pulled down underneath that pattern there. Let's add some wavy little lines of black up here, because sometimes old ocean plate actually gets folded up into these mountains. You can find seashell fossils all the way at the top of Mount Everest, the tallest mountain in the world. So Mount Everest has limestone and stuff at the very top. There are all these folded, blended together layers. Some of them are metamorphosed, some of them are just folded and changed in position, but it tells a story. It tells a story of the ancient crust being pulled up. And all this stuff has got earthquakes going on because it's a very violent collision, but it's a very slow collision. We're talking, remember, that plates only move about the rate that your fingernails grow. Very, very slowly over time. Okay, I'm just going to add some final touches in here. And that should be almost done. Since this is the tallest mountain in the world, just for the sake of it, let's put some snow on the top of that mountain. A little bit of white, a little bit of snow. Because we know these tall mountains are peaked with snow. Alright, so that is our convergent continental to continental slamming together, forming the tallest mountains in the world. All these folded rock layers, some igneous intrusions from that melting upward movement of magma, the old ocean plate still subducting underneath. It'll eventually get recycled into the mantle, and that mantle convection driving this whole process. Alright, so that concludes our convergent boundary diagram. We only have one more diagram left, so